Next up on our discussion on elasticity or elastic properties of materials, we have Hooke's Law. A spring is an example of an object whose design and construction makes it more elastic than the material it is made out of. Suppose we have a spring and we apply a force F to stretch the spring. So we apply force F to stretch the spring by distance x from an unstretched position. We refer to the unstretched, uncompressed position of the spring as the equilibrium position. X is equal to 0. Because of the applied force F, the spring will be stretched by distance x. F and x are found to be proportional to each other. The force F is proportional to the deformation, to the stretching that it produces in the spring. So F is proportional to X. We can make it an equality by using a constant of proportionality. Let the constant of proportionality be K. F applied is equal to Kx. Where K is our constant of proportionality, we refer to K as the force constant, and it has a unit of Newton per meter. If we look, X is heading to the right, same direction as the force F that produced it. Thus, in vector form, F applied is equal to Kx. In vector form, you have F applied is equal to Kx. Vector F and vector K, vector X, they have the same direction. If the force was stretching the spring, the deformation will be heading in the direction of the force. The spring will be stretched in this direction. If we are compressing the spring with force F in this direction, the deformation will also be in this direction. F applied is equal to Kx. Now, the spring will react by applying a force of its own. Third law of motion, for every action, there is an equal but opposite reaction. So the spring will react by applying force F spring, same magnitude as the applied force, but opposite in direction. Thus, we have F spring is equal to negative Kx, same magnitude as F applied, but opposite in direction, minus. Okay? Note that minus sign does not mean negative direction. It means opposite direction of X. Since X is heading in this direction, F spring will be heading in the opposite direction. F spring again is equal to negative Kx. Magnitude, you just remove the direction. We have F spring is equal to Kx. F spring is equal to negative Kx. This is what we refer to as Hooke's Law. And K now, we refer to as not just the spring, the force constant, but rather we can now refer to K as the spring constant. And it's a property of each spring. Each spring has its own value of K. The spring constant, also known as the force constant. Just like gravity, spring force, or we may refer to it as the elastic force, spring force or elastic force, as it turns out, is a conservative force just like gravity. And just like gravity, work done by the spring gets stored in the form of potential energy. In this case, elastic potential energy. Suppose we stretch the string from equilibrium position x is equal to 0 to a final position x. As the spring is being stretched from 0 to x, the spring is performing work. The work done by the spring is given by integral of f spring dotted with dx. Using our equation for f spring is equal to negative kx. Integral of f spring dotted with dx will give you work done by the spring is equal to negative 1/2 kx squared. And this work done gets stored in the form of elastic potential energy. Thus, the work done by the spring is equal to negative delta EPE, elastic potential energy. So, negative change in elastic potential energy. The work done gets stored in the form of elastic potential energy. Thus, work done is negative 1/2 kx squared. The elastic potential energy is given by 1/2 kx squared. And this elastic potential energy is energy, thus its unit is unit of energy, Newton meter or joule. And this energy, elastic potential energy, is just one more energy to consider when you are doing energy analysis. When you are performing conservation of energy analysis, kinetic energy initial plus potential energy initial plus work done by external forces is equal to final kinetic energy plus final potential energy. In terms of the potential energy terms, we now have two potential energy to consider: gravitational potential energy and elastic potential energy. Just like when we were covering the angular motion topic, we had two kinetic energy to consider: the linear kinetic energy and the angular kinetic energy. Now, for potential energy, we have gravitational potential energy and elastic potential energy. So, the equation now becomes kinetic energy initial plus gravitational potential energy initial plus elastic potential energy initial plus work done by the external influences is equal to final kinetic energy plus final gravitational potential energy plus final elastic potential energy. And that's it for now. We'll continue our discussion in the next video. In the next video, we'll finish up our discussion on elasticity by looking at a few examples. So once again, that's it for now. Thank you for watching.